Good afternoon, everybody. Coming at you solo here from the prep room in the science building. I am here to talk with you today about intermolecular attractions and properties related to intermolecular attractions. Ideally, if you were able to locate some rubbing alcohol at home, you have already done a little experiment where you dipped a finger or splashed a little room temperature rubbing alcohol on one hand and a little bit of room temperature water on the other hand, and compared the way those two things felt. Even though both were at the same temperature, the rubbing alcohol should have felt cooler. And the reason for that, as you may have figured out by now, is that the rubbing alcohol evaporates faster than the water does. Evaporation is a cooling process. We'll see why that's the case in just a little bit. And that cooling happens faster when the evaporation is faster. And so that one feels colder, even though, once again, the liquids were at the same temperature. I'm here in the prep room with you to show you a little demonstration that we can do when we have some high precision balances like we do, to compare two more liquids, or well, one of the same ones. This is acetone, and here is some water. I'm just going to prepare two dishes there, the acetone and the water, and put both of those on the balances. So I'm going to put water on the balance over here, and if we try to weigh that dish of water, so there it is. Note that we can see the mass changing as it sits there. Changing very slowly, way out there in the 10,000ths of a gram place, but nevertheless changing, going down as water evaporates from the dish. So those actual water molecules that are leaving the dish are slowly decreasing the weight or the mass of that sample of water. The acetone over here, I'm going to put onto the other balance and close the door there. And over on this balance, we can see the mass decreasing much more rapidly as acetone evaporates more rapidly than water. Why does acetone evaporate more rapidly than water? Well, we need to know what acetone is, and we're going to come in here and take a look at a Lewis structure. So here is a Lewis structure for acetone, and you can see we've got a central carbon atom there, a trigonal planar arrangement around it with an oxygen double bonded, a couple of carbons with some hydrogens attached. I've drawn the indication of a polar bond there between carbon and oxygen, because that is a pretty strongly polar bond. And so that does make acetone a polar molecule. So we've got some intermolecular attractions going on there of the dipole-dipole variety. Water, of course, you know, is also a polar molecule, and I've drawn there the hydrogen bonding that we know goes on between water molecules. Would acetone have hydrogen bonding? Let's look back at that structure. It's got hydrogens, it has oxygen, but once again, as we've seen before, this is a case where the hydrogens are not directly bonded to the oxygen, and so they are not having their electrons drawn away strongly enough to enable them to do hydrogen bonding, and so acetone is polar, but no hydrogen bonding, lowering the strength of its intermolecular attractions as compared to water and making the acetone evaporate faster. Why do smaller intermolecular attractions mean faster evaporation? And for that matter, what exactly is evaporation? How does evaporation happen? If we were talking before about phases, and some things are gases because of low intermolecular attractions, other things are liquids because of high intermolecular attractions. How does something go from being a liquid to a gas without changing its intermolecular attractions, or changing its temperature to heat it up or cool it down or whatever? Let's look at that. So we're going to take a little stroll in here, go past my kids' artwork from the other day, and here we go. So this is something we have seen before. This is a kinetic energy distribution curve, and you may recall this is our way of showing in a sample of material how all of the particles in that material have different kinetic energies. There's a range of kinetic energies. The average kinetic energy located just to the right of that peak will be proportional to the temperature of the sample, and so I've drawn two curves here. the one in black showing a low temperature sample, the one in red showing a higher temperature sample that I forgot to write in high T in red. Over on the right-hand side of this kinetic energy distribution curve, though, we've got a new feature that we haven't talked about. Basically, if you've got a sample of material and those particles all have different kinetic energies, they're all moving around and it's in the liquid phase, and so the kinetic energies are not high enough to overcome the intermolecular attraction for the most part. You still, though, have some molecules with much higher kinetic energies. And so those much higher kinetic energy molecules can actually escape the attractions of the surrounding molecules. So one of those molecules, as it's heading towards the surface, reaches the surface, and rather than being pulled back in by the intermolecular attractions, just breaks right away and goes on into the gas phase. Well, for a given liquid, that amount of kinetic energy needed to escape depends on the strength of the intermolecular attractions. And so what I'm showing you on this right now is how that temperature dependence affects the rate of evaporation that you would have. I didn't show on this how the strength of intermolecular attractions is related to that. I can draw that in right now. We're getting a little dizzy with this. I was not prepared to do this right now, but for a molecule like acetone that has smaller intermolecular attractions, the energy needed to overcome those intermolecular attractions is less. And so that would give us a vertical line like right here, say. Okay, so now what are those shaded regions? Well, for calculus reasons that we don't need to get into, the total area under any one of these curves would represent the total number of particles in the sample. And so the shaded area to the right of that vertical line, to the right of the energy needed to escape line, is representing the fraction or the number of particles that have enough energy to escape out of the total. So those particles have enough energy to escape. All the ones that are not shaded over there don't have enough energy to escape. And so a couple of things going on here. If the energy needed to escape is smaller, like I've done with the green line here, then we'll have more particles that have enough energy to escape. More total and a bigger fraction of the full sample of the liquid. Similarly, if we raise the temperature of the liquid, we look at that red curve, raising the temperature will shift the kinetic energy distribution so that a higher number of particles have enough energy to escape intermolecular attractions, a higher percentage of the total have enough energy to escape intermolecular attractions. And so that means the evaporation, that escaping of molecules, goes on at a faster rate. Okay, so now, what does that mean then about, well, I guess some other things that we're going to get to. Let me take you over here and let's consider the phenomenon of liquid vapor equilibrium. Liquid vapor equilibrium is something we've talked about before, but we want to get into it in a little more detail right now because of a phenomenon that we're going to look at. So liquid vapor equilibrium. Imagine we've got a closed container, and this is our low temperature closed container, and it is filled with a liquid, and that liquid is evaporating at a particular rate. That up arrow there is meant to represent the rate of evaporation. As time goes on, there's my time axis, as time goes on, we will have more particles in the vapor phase. So first we had no particles in the vapor phase, it was all liquid. Time has passed, we have now evaporated some of those liquid molecules. We have some vapor there, and now that we have some vapor, some of those vapor molecules can get recaptured by the liquid, and we have a small rate of condensation represented by that little arrow there. As long as evaporation is happening faster than condensation, though, there will be net creation of vapor. And so in our next picture, there's even more vapor than there was before. Because there is more vapor, there is a faster recapturing of vapor. And so the rate of evaporation, or I'm sorry, the rate of condensation has increased. So comparing those two pictures, time has passed, more vapor has collected, the rate of condensation has increased. And you'll note now that the rate of condensation is equal to the rate of evaporation. Once those rates are equal, there won't be any more change in the total amount of vapor there. We have reached a state of equilibrium. The vapor up in there now exerts a pressure. Because there's not a lot of it, the vapor pressure, the equilibrium vapor pressure of that liquid is fairly low. If, on the other hand, we have a liquid that has a higher initial rate of evaporation. I did this one as a high temperature liquid, so it could be the same liquid at a higher temperature, or a different liquid that has weaker intermolecular attractions at the same temperature. Either way, if we have a high initial rate of evaporation there, as time passes and we build up vapor and increase the rate of condensation, build up vapor, increase the rate of condensation, we have to get more vapor present in that container before that rate of condensation equals the rate of evaporation. So comparing this one to that one, we have a lot more vapor in the container down here to get a condensation rate equal to that bigger evaporation rate. And so with more vapor present, because pressure is proportional to number of moles of gas around, more vapor pressure or more vapor present means a higher vapor pressure. All right, so now what does that mean? Well, let's look at the temperature dependence of vapor pressure. Here's a graph where the black curve represents water and water's vapor pressure at different temperatures. If you want to pause the video for a minute now, you can go look up vapor pressure of water, either a table or a graph like this, and then come back and compare to what I have right here of all the vapor pressures of water that you see. So first of all, you note that it increases as the temperature goes up for reasons we just said, and it does not increase in a linear fashion. There is one particular vapor pressure that is special to us, and that is the vapor pressure at 100 degrees Celsius. At 100 degrees Celsius, the vapor pressure of water is 760 torr, or 1 atmosphere. The significance of that has to do with a phenomenon that we see all the time, and that is the phenomenon of boiling. Evaporation and boiling are both liquid passing into the gas phase, but they are in a sense different. And the reason that they're different is evaporation happens just all the time at whatever temperature you're at, but boiling is only happening once we reach a certain temperature. How do we know when something is boiling? What's the big feature that differentiates boiling from evaporation? Well, here we go. I've got some water boiling on my hot plate right here, and you can see there the bubbles that are characteristic of boiling. So there's boiling going on with my temperature probe, 99.6 degrees Celsius. Not a bad calibration of that temperature probe. All right, so bubbles. The bubbles happen, the bubbles form when a liquid boils. Evaporation happens just at the surface of the liquid. Boiling happens in those bubbles. Why does boiling happen in bubbles, and why does boiling happen when the vapor pressure of the liquid equals the surrounding atmospheric pressure? Let's take a look at a drawing of a bubble in a boiling liquid. So bubble drawn much bigger obviously than we see them there, but just to get the idea of what's going on. When a liquid is boiling, the bubbles that form are not air bubbles, as some people think, but bubbles of vapor of the liquid itself. So before, we were looking at a diagram of a closed container and reaching liquid vapor equilibrium in a closed container. Well, this bubble of vapor within the liquid is sort of like a closed container. Here's the vapor space, and there's the liquid space around it, and that vapor can't escape out. And so that vapor can be in equilibrium with the liquid around it. All right, so now imagine that we've got a liquid that is at a pressure, that is at a temperature where the vapor pressure of the liquid is something less than the 1 atmosphere of atmospheric pressure. If the vapor pressure of the liquid, that's the pressure exerted outward by these vapor molecules in the bubble, is less than the atmospheric pressure inward, that inward pressure is going to be pushing harder than the outward pressure, and that bubble just collapses, or more to the point, it never forms in the first place. Once the water gets to a high enough temperature, or the liquid gets to a high enough temperature, that the pressure exerted by the vapor in equilibrium with the liquid is equal to the surrounding atmospheric pressure, then that bubble can withstand the pressure, the bubble forms, and the bubble rises up to the surface and releases gas. And that's the boiling that's going on. You might be wondering, wouldn't the pressure be a little bit lower down below the surface, or sorry, a little higher down below the surface of the liquid? And yes, that's true. Deep in the ocean, water's boiling point is much higher than it is up at the surface. In a beaker like this, though, the pressure at the bottom of that beaker is essentially the same as the pressure on the surface of the liquid. You may also wonder, why do the bubbles form at the bottom if that's where the pressure is the biggest? And the answer to that, of course, is that's just where they're closest to the heat source. And so the water is hottest there at the bottom of the beaker. But if I were stirring that, we would see more boiling all over as opposed to bubbles just forming at the bottom. All right, so boiling point and vapor pressure and rate of evaporation then are all things that depend on the strength of intermolecular attractions. One last thing on all of this that I think you'll find interesting. I guess maybe two last things on all of this, since I drew both of those things on here. First of all, the green curve I drew is a curve, a different vapor pressure curve for a different liquid. This is a liquid that has a higher vapor pressure at every temperature than water has at that particular temperature. So this is a liquid that has a higher rate of evaporation than water at a given temperature, and so it takes more vapor to reach equilibrium, and so a higher vapor pressure. So something that evaporates more easily, a more volatile liquid. In particular, this one is the acetone that we were looking at. Note that not only does that mean that it evaporates faster, that also means that its vapor pressure reaches 1 atmosphere at a lower temperature than the temperature at which water's vapor pressure reaches 1 atmosphere. And so acetone has a boiling point of 56 degrees Celsius, much lower than water's. By the way, that boiling point of water I labeled not just boiling point, but normal boiling point. And the reason we call that the normal boiling point is because that's the boiling point at normal 1 atmosphere of pressure. But of course, if water were under a different pressure, then it would boil at a different temperature. So every point on this curve is actually a boiling point for water. One example of this that you may actually have in your home and be able to try out at home if you want is what goes on in a pressure cooker. A pressure cooker is a device where the water is in a pot that is closed off, and so as that water heats up and the vapor pressure builds up above the water, because it's a closed pot, that vapor doesn't go off and pressure builds up above the liquid. The pressure in home pressure cookers can get up as high as 2 atmospheres, I've read. So this y-axis, obviously not to scale there, but can get up to 2 atmospheres. At 2 atmospheres, the vapor pressure of water, the temperature at which water has a vapor pressure of 2 atmospheres is 120 degrees Celsius. And so if you get that external pressure up to 2 atmospheres, the water has to reach 120 degrees Celsius before it is at a vapor pressure high enough to create bubbles and be boiling. And so in an open pot, because that boiling water never gets above 100 degrees Celsius, anything that you're cooking in the pot is going to be 100 degrees Celsius. In a pressure cooker, you've got the water in there not boiling all the way up to 120 degrees Celsius. And so you can be cooking things at a much higher temperature than you would be in the open pot, which allows things to cook faster. And that actually gets into our next topic of kinetics. But that, I think, is enough for this lesson. So signing off from the Manning Science Building 3rd floor at Woodbury Forest. Take care, everybody. I will see you again soon. Bye.